Hi everyone, I'm Jian Zhongshu from China. Welcome to the talk of DeFiWarder, protecting DeFi apps from token leaking vulnerabilities. Our authors are from Sun Yat-sen University, Andy Group, and Zhejiang University. At the beginning of the presentation, I would like to talk about the background of our work. Recently, attacks on vulnerable smart contracts have resulted in severe financial loss. For example, Slowmik reported that the total amount of money lost due to blockchain attacks is over $30 billion, most of which are due to smart contract bugs. However, as the functionality of smart contracts become more complex, complicated bugs are emerging and always exploited to attack, especially the functional bugs that related to the specific business of the DeFi apps. In this talk, we summarize token leaking means that an entrusted user could abnormally withdraw funds far exceed his deposits. Actually, there are several root causes for token leaking. On the one hand, the common bugs such as integer overflow, access control, and control flow hijack. On the other hand, the functional bugs such as price manipulation bugs and improper token transfer. Since token leaking vulnerabilities are always exploited in attack incidents, we attempt to address them. Since the final exploited result of bugs are token leaking behaviors, we attempt to recover token flow of DeFi apps and find out the users that perform token leaking. Assume that someone deposits X tokens and withdraws Y tokens. If X far less than Y, the user may trigger a token leaking bug and obtain abnormal return rate. With this workflow, we hope to root all the cases of token leaking. However, there are some challenges for this workflow. First, as shown in the figure, the edge means the fund flow. We can see that there are several fund flows in a single transaction. Many of them are not related to user and the DeFi app, which make us hard to distinguish the fund flow between user and DeFi app. Second, in this figure, the different colors of edge means different kinds of funds, which make us hard to determine the value of funds and perform further analysis. Third, the functionality of a DeFi app that allows users to earn interest makes us hard to identify true token leaking. In other words, users can legally withdraw more funds than their deposits rather than token leaking. Next, I would like to introduce the designs of our work. To this end, we propose DeFiWarder based on the above-mentioned idea. It tracks token flow between users and DeFi apps, and finds the relations between users. Based on them, DeFiWarder reviews the abnormal token flows as token leaking behaviors. At stage 1, we use the instrumented event to recording trace from raw transactions from Ethereum. The trace is arranged in a core flow tree. The ball in tree means transaction, including the external transaction and its derived internal transactions. The double circle means the event emitted by smart contracts, such as the token transfer, and the edge means the derived relationship between the nodes. Based on the core flow tree, we perform in-depth analysis. Before stage 2, I briefly introduce some common deposit modes in DeFi apps, and the withdrawal modes are similar. The first mode is straightforward. User A call and transfer token to the process contract, so we can easily capture the token flow between user and the DeFi app. The second mode is that user A call process contract but transfer token to another contract, the vault contract. In this case, we need to know the true vault contract for extracting the true token flow. The third mode is that user A call process contract and the token is transferred from user B to process contract. In this case, there may be a relation between user A and user B, and user A can withdraw funds based on the deposits of user B. If we do not know these relations, we will report false positives since user A withdraw funds without disposing any funds. In general, the complex deposit and withdrawal modes bring barriers to extracting token flow. and they require us to capture the relations between users for more precise analysis. At stage 2, we first mine the row of address. We tag the address as user or app, given the address of TX origin and process. If a new transaction is triggered, the COI is marked with the same row as caller if the COI has not been marked with any row. In this way, we obtain the rows of address. Then, based on LP tokens, we construct relations of the address with user rows. If user A deposits tokens and the LP tokens are mined for user B, we record the relation between user A and user B. And if user A transfers LP token to user B, we also record the relation between user A and B. Overall, in stage 2, we first perform heuristic row mining to find out the rows of address. Then, we track token transfer between user and DeFi apps as token flow, and construct the relations between users. This figure represents the token transfers of a single transaction. The red nodes are user rows, and the yellow nodes are app rows. We chart the token transfers between red nodes and yellow nodes as token flows. The red nodes in figure are both user rows. We also construct the relations between them. At stage 3, based on the mighty relations, we first group the users with relations and gathering their token flow. Then, we unify the value of token flow in different tokens based on exchange rates in Uniswap v2. Finally, we evaluate the normal return rate of the DeFi app. If the token flow has a return rate greater than the normal rate, we consider it as a token leaking behavior. Next, I would like to introduce the experiment of our work to evaluate the effectiveness of our DeFiWarder. In our experiment, we set up 3 research questions to completely evaluate the performance of DeFiWarder. We evaluate the effectiveness of DeFiWarder and other existing tools, and we also evaluate the efficiency of DeFiWarder. To conduct our experiment, we set up our dataset based on historical security incidents from May 2020 to June 2022 that caused by vulnerabilities. The table lists the details of our dataset. They involve several kinds of root cause, such as the common contract flow hijack and price manipulation bug. In RQ1, DeFiWarder successfully detects 25 token leaking vulnerabilities from the historical transaction of 30 DeFi apps. In addition, the precision rate is 72%, which is acceptable in practice. Furthermore, DeFiWarder detects all token leaking caused by price manipulation bug. In RQ2, since existing tools such as Lisa, we still cannot directly detect token leaking. We evaluate their effectiveness in detecting the root cause of token leaking. Existing tools cannot handle the functional bugs such as improper token transfer, and they only detect contract flow hijack in 4 vulnerable DeFi apps. The result means that they have limited performance in addressing token leaking vulnerabilities. In RQ3, we evaluate the efficiency of DeFiWarder. It only has a minimal overhead, consuming only 12% more time than the original EVM. The TPS of DeFiWarder is 183.2, which is greater than the TPS of Ethereum, 12.4. So, we conclude that DeFiWarder has the ability to perform real-time monitor on Ethereum. For example, some apps are attacked in multiple transactions. DeFiWarder can review the first one so that we can take measures for protection. In the next part, I would like to conclude our work. First, token leaking vulnerabilities are important and common in DeFi apps, which are worth our notification. Second, tracing token flows and user relations are effective to protect DeFi apps from token leaking vulnerabilities. Third, existing tools are not useful enough for detecting token leaking in practice. Finally, I sincerely thanks to the reviewers and all researchers who have participated in the discussion and conference.